Welcome. In this particular lecture we're going to have a look at alpha blending. It's one of the components within our graphics coverage, and it's concerned with how we can combine two images together. So normally a source image that we're drawing on top of a destination image. We'll start off by having a look at alpha compositing, which is, I suppose, the graphics theory which surrounds how we do combine two images. In terms of that theory, alpha blending or alpha compositing, as mentioned, it's concerned with how you take one image, your source, combine it with a second image, destination, which really is there, and what is produced in terms of the output is this process of compositing. And there's actually quite a lot of ways of doing this. The most common way you can see listed on the screen here, that we are interested in taking the source color and multiplying this by some blend function. This will determine how the thing gets to be combined. And adding that to the destination color, what we already have there, again, as multiplied by some blend function. And typically we apply each channel separately. So we will combine the red channels separately to the green channels, to the blue channels, to any alpha channel that we may have available. There's actually quite a wide range of different blend functions that can potentially be used. So you can see a number of them listed here. You have 0 for each component is multiplied by 0 itself, which means you don't get any of the source to destination appearing if it's multiplied by 0. To 1, where each component is multiplied by 1, so you retain the full component. 3 other ones, source color, source alpha, destination color, destination alpha. The ones that we will be inclined to use are things like source alpha, where each component of the color is multiplied by the alpha value of the source. So you may have a red value, say of 0.5, so it's a mid-strength red, and you would multiply that by the alpha value for that particular pixel, and that determines how much appears. So source alpha we'll use, 1 we'll occasionally use if we want to retain the full image. It's also worthwhile saying for most of these there also is the inverse function. So alongside source alpha we also have inverse source alpha, which is 1 over it. So it's, if you like, it's the inverse. You multiply the two together, you'd end up back just with the normal value. For us, when we're considering 2D games, there is only 2 forms of combination that we are particularly interested in, and you can see the examples of what they look like shown on the screen here. Admittedly, it's a 3D render, but nonetheless it does convey the type of 2D compositing that we're interested in. The first one is just known as normal alpha blending. So when we talk about alpha blending, normally this is what we have in mind. And it's drawn a transparent or translucent image, one that you can see through to a certain extent, so that you appropriately see what is underneath. And depending upon the strength of the alpha value, it'll be more visible or less visible. The second type is known as additive blending. And here we're going to add one image to another image. And generally we would do that to brighten up the destination image. So we can use this to brighten, to simulate light, for example, as one of the applications. We'll have a look first of all with alpha blending before then moving on to additive. And on the top, towards the right hand side, you see the particular formula or blend that provides normal traditional alpha blending, where the destination color, each of the channels, is equal to the source color times the source alpha plus the destination color times the inverse source alpha. And we have a table down at the bottom that will explain or help sort of identify this. So if we have a source alpha value of 1, which means we want the source to fully appear and the destination to be completely ignored, it means that for the color then we'll be multiplying the source color by that alpha value of 1 in order to fully retain it. And we'll be adding onto it the destination color times inverse source alpha. That's 1 minus the source alpha. So 1 minus 1 is 0. So we're adding on 0 of the destination color, which is fully the source color. If we had a source alpha value of 0, then it's the other way around. The source color multiplied by 0 gives you 0, plus the destination color multiplied by the inverse of that, which is 1. So in other words, we just end up with the destination color. If we had an alpha value of 0.5, see here that we keep half of the source value and we add to that half of the destination value. And that gives us then the translucent effect, where we're seeing a bit of the destination and a bit of the source images. So fairly straightforward, and that's how we actually bring about normal alpha blending. Important little aside here, if we are using alpha blending, it is essential that we draw things in the right order. If we have two images that were drawn onto a background and both of those images are transparent, then the order in which we draw them will actually make it visually look different. And it can be a little bit hard to see, but we've got a couple of squares, sort of yellow and bluey squares down in the bottom left-hand corner. They are actually drawn in a different order, and if you look at the overlap, there is a subtle but nonetheless visible difference in the colour that is drawn. So we need to be careful when we're drawing transparent images about the order in which we draw them. Next up, we're going to have a look at additive blending as our second common form of compositing. Additive blending, it's less commonly used, but nonetheless it's used quite often. It has the form of blending that you can see here, where the source colour is multiplied by the source alpha. So depending upon the alpha value, we'll retain the source. And we are adding onto that the destination colour times 1. So in other words, we retain all of the destination colour and we add in onto it the source colour. That's where the name additive comes from. Now, why would we do that? A few reasons. One thing to say about it is commutative, which means that the order in which we actually combine these doesn't matter. We'll end up with the same value overall, and that's a useful enough property for it, particularly when we're using it in a particle system, because we just want to combine a whole bunch of these together and to get a particular output. There's no need to sort by depth order if we're drawing this way here, so it is a distinct advantage. The only downside is that it is additive, that if we were, for example, to add red to green to blue, and this is similar with light, we would end up with a white colour at the end. So it's more, or it can be more difficult to visualise what the final output colour is going to be, because you need to sort of think about the colours added together, and that's not always intuitive as to what that final output will be. So we've got an advantage. Why would you use additive blending? We'll see so in the next slide. In terms of uses, two big uses that we could use them for. One is for particle effects, and you see a couple of particle effects over on the left-hand side of the screen. And for things like explosions, what we are doing here is taking a simple image and we're drawing it multiple times additively, because that then builds up the intensity of it. And as they sort of spread out, naturally the intensity will decline because we're drawing less one on top of the other, and then the explosion fades out. So it's very, very useful for particle effects. It's going to be one of the key mechanisms whereby we can render our particle effects. The second use, and this very much is specific and dependent upon the game, you can actually use it to provide cheap and cheerful lighting within 2D games. So if we had a light source that was flickering on and off, we could simulate that by drawing, if you like, say, a triangular shape for the cast of the light, but combining it using additive lighting. So key takeaways to this, we've got a few of them. Alpha compositing is the general theory that we're talking about here, where we draw a source image on top of a destination background image. Normal alpha blending is our standard way of combining a translucent or transparent image so that it looks right based on the background. And for some games, or for some particle systems, we may end up using additive blending to provide some notion of lighting effects or particle effects. So that's all we want to talk about here. Not a huge amount of context and theory to this, but in terms of certainly how we combine our graphics, this is going to be a useful way of building up our graphical effects.